Hello geometer friends, it's Miss Backfish and I'm making this video for you to show you a little bit about line symmetry and rotational symmetry, two symmetries that are really important in geometry and actually in algebra as well when we talk about functions that are even or odd or neither really. But specifically right now we're talking about line symmetry and rotational symmetry in the context of geometry. So I made this little worksheet thingy just to demonstrate and talk about it a little bit. First of all, sort of defining it. A figure has line symmetry if there exists a line that divides the figure into two congruent parts, such that one can be mapped onto the other by a reflection across the line of symmetry. Now, let me tell you why I added that part. Let's say, for instance, the last little phrase. Let's say, let's not do this actually. I'm going to draw a parallelogram, but I want to draw one a little bit more distinctly different in terms of the two directions. And I'm sorry it's lopsided, but that's really okay. I'm not really worried that much about lopsided. If it weren't lopsided, if my parallelogram were more perfect and I drew a line right down the middle of it, then I would be dividing it into two congruent parts. However, that's not a line of symmetry, because if I take this side and reflect it across the line, let me make that a little darker so you can see it a little better, it would be somewhere like this. Somewhere in here. It would not be over there where actually that triangle is. So you can have something, you can have a line that divides your figure into two congruent parts that's not necessarily a line of symmetry or giving your figure line symmetry. So it specifically has to be so that basically I can reflect one side over and it lands on top of the other side. So this figure right here has a line of symmetry right down the middle that's vertical here, because these two parts, here and here, could be reflected, either one of them could be reflected across that line and it lands right on top of the other one, meaning it maps onto it. Okay, same thing here, except this time we have two lines of symmetry. We have a vertical line of symmetry, saying that I can reflect either of these two sides onto the other perfectly, or we've also got a horizontal line of symmetry, saying that I could take the top of this and fold it down over the bottom and it would match up perfectly. This one has no line symmetry. So line symmetry is really just the kind of symmetry, symmetrical, that you learned about in kindergarten. So if we have lines of symmetry, it's just the normal kind of symmetry you think of. So we have to figure out, it's basically like, can I fold this figure fold it in half on top of itself across this line. So these various figures I put down here were just some to look at the line symmetries of each one. So this one right here looks a little bit like a red cross. I would say that it seems to have a line of symmetry vertically right down through the middle. I think it also has one horizontally right here. I'm also seeing two other lines of symmetry. See if you can figure out what I'm thinking of. I would go ahead and say that there is also a line of symmetry that goes right here. And another one that goes right here. So basically, if I folded the figure over any of those lines, the two sides would meet perfectly. Okay? Now let's look at this figure in the middle. Line symmetry. Well, clearly, if I were to divide it right down the middle like this vertically, that's not going to work because we have a pointed side over here and it's not pointed over here. There's only one line of symmetry that I can see in this one. Where is it? You're right, and I can hear you through this recording. Isn't that amazing? It's right there through the middle, horizontally, and much straighter than the one I drew. I actually got out one of my favorite straight edges to use for this and have been forgetting to use it, so I will try to use it on the next one. One of my favorite things to use as a straight edge is an old gift card or hotel room key. They make a perfect straight edge. So looking at this star right here, I'm going to use my perfect straight edge to make a line of symmetry, or two if I can find any. Okay, think about whether you have any lines of symmetry in a star. It helps on this one perhaps to picture it as like a person, where this is a pointy head, two arms, and two pointy toes. Well, right down the middle of a person, there's a line of symmetry. So we've got a line of symmetry here. I'm not going to make it dotted because it's a little bit easier to do this here. But then I can turn this star lots of directions and have a point at the top that I can think of as the head of my person. So, although it looks like it's not exactly symmetrical here, but that was me doing it with my clip art. And that's my fault. We're going to pretend it is. So basically there's a line of symmetry each one of these. You could think of it as there's a line of symmetry that goes through each tip, each point of the star. So how many does that make? We have 5 lines of symmetry. We've got 1, 2, 3, 4, 5. This is the bottom of the first one, so then that's the same line. All right, next we have this band symbol, not B-A-N-D, B-A-N-N-E-D. Okay, like if I'm going to ban you from doing something. Or I could ban ghosts, because this looks like the Ghostbuster symbol. Okay, so this looks like it has at least 1 line of symmetry. How many can you think of? I'm going to say there are 2. I see a line of symmetry right down through the middle here, like this. And I also see one going perpendicular to that. So I think I have 2 lines of symmetry there. Last but not least, I've got a Star of David over here. Or you could think of it as 2 triangles on top of each other. All right, this is full of symmetry, this one is. Again, assuming it's perfect. This one looks a little bit vertically squished, but pretend it's not. Pretend that this is a nicely symmetrical Star of David. And we've got basically through any point of the star and the point across from it. There we have it. Yeah, it is a little bit lopsided because this side doesn't look perfect, but we're good at using our imaginations here, right? Okay, so each tip, each of these 6 points on this 6-pointed star, we can go straight through that line and go through the tip across from it. We could also go across or around this star, making lines of symmetry, if I can find my words right, through kind of the valleys in between the tips. In other words, this and the one across from it. Like right down through there. And down through here. And across here. So I've got symmetry all over the place in that. How many lines is that? Well, I've got 1, 2, 3, 4, 5, 6. Notice that on a 5-pointed star I had 5, and on a 6-pointed star I have 6. So that's line symmetry. Now, another type of symmetry that we get a little bit more interested in now is rotational symmetry. So again, I made up a little blurb about it, and I said a figure has rotational symmetry if it can be mapped onto itself by a rotation of less than 360 degrees. Basically, if I want to turn anything in the entire world all the way around, it looks the same as it did before I turned it, theoretically. I guess something could happen during that turn. But the point is, the fact that it looks the same when I turn it 360 doesn't have any meaning. We're interested in, does it ever look the same when you turn it less than a full turnaround? The minimum number of degrees it must be turned before first mapping onto itself is considered the angle of rotational symmetry. The order of the rotational symmetry is the number of positions all the way around the figure at which a point maps onto itself. When we talk about order, we do include what if it's all the way around. Okay, so we do include that starting point as one of our points of symmetry. Sometimes we are asked to provide all angles at which a figure maps onto itself, in which case we do not include 360. Okay, so here, looking at this, it says the angle is 180 and the order is 2. So this is clearly meant to look squished vertically, so to speak. It's wider this way than it is this way. So it's not just a printing issue. That's what it's supposed to look like. So if I took that figure and I flipped it completely upside down, that's what 180 means. I did a rotation of 180. It would look the same. So I'm going to use transparency to demonstrate that. Let me trace it. And again, we're not going for perfection here. We're going for a big idea. If I take that and I rotate it, and where am I rotating it? Well, if I rotated it like around this point, then no, it's leaving. It's not going to map up onto itself if I do that. So we're not talking about that. We're talking about rotating it about its own center, rotating it in place. Okay? And I'm talking about like this. If I can hold that still. All right. So this is 180. Sometimes it helps to keep track. Let me put it back. Sometimes it helps to keep track of where you started by giving yourself a little reference. Okay, this is up. So after I spin it all the way around to where that's pointing downward, it matches. That's the first mapping. So that's 180 degrees because I've gone from the arrow pointing up to the arrow pointing down. And yes, when I turn it all the way around, it matches again, but that's not really rotational symmetry. That's just life. That's just what happens when you turn something all the way around. Okay, so let's look at this triangle beside it. Equilateral triangle is what it looks like. And let me address this real quick. 180 we talked about. 2, the order of 2 basically means there are 2 positions if I go all the way around, including starting place or the ending place. I don't want to count it both times, but there are 2 positions at which it looks the same, like this, and exactly upside down, like this. So that's why it's called a rotational symmetry of an order of 2. Okay, so let's look at this triangle. It says that we have rotational symmetry with an order of 3 here. So that means we're talking about there are 3 positions at which it looks exactly the same. So let's go ahead and make a little asterisk to point out, okay, this is what it looks like when it's straight up, or this is with the asterisk up above the triangle. If I turn it pretty much a third of the way around, it matches up. That's the second place it looks the same. And if I turn it another third of the way around, which is 2/3 of the way around, it matches up again. So that's the 3 places that it looks like exactly the same figure as we rotate. This is back to the first one I counted. Notice that if I divide 360 by this number, the order, what do I get? I get 120, which is exactly what this says. It says that after I've rotated at 120, that's when I get to the first point at which it matches up. Same thing over here. If my order is 2, then my angle of rotational symmetry is 180 because 360 divided by 2 is 180. This one has no rotational symmetry. Let me give it some space here. Okay, if I rotate this around on top of itself, nowhere does it map up. It doesn't look right. It doesn't get right on top of itself. So sorry, this is not the most accurate way to do this, sorry. I think you can get the idea pretty well though. Here is a 180. Notice it's not matching up. Now, where does it match up? Until you get all the way back around, which, like I said, that doesn't really count as having rotational symmetry. Okay, so let's look at these same figures we used for the line symmetry. All right, this one that looks like a red cross arrow. How many places all the way around does it look like it would look the same? Let's try. Now I'm going to put something on the top. I've used an arrow and a little asterisk. Let's use a little heart this time, just to remind me that that's where I was when I started. Okay, let's see if I can spin this a little bit more effectively or efficiently using a pen, or excuse me, a pencil as my center. There we go. Okay, that's my center of rotation. If I turn it so that the heart is at the side, it matches up. Well, if the heart started at the top and then now the heart's at the side, I've rotated it 90 degrees. So after 90 degrees, it matches up. And again, when the heart is at the bottom, that means I've gone 180 now. And it's also going to match up, I can get out of the way of the camera, at 270. And then we get back to our starting place. Okay, so including the start, and then when the heart was here, the heart was here, and the heart was here, there were 4 places at which it looks exactly the same. Not counting the heart, because the heart's not really part of the shape anyway. So that has an order of 4. Okay? Now, if it has an order of 4, what's the minimum angle? Well, we said up above here that if I divide 360 all the way around by the order, I find out what the angle of rotational symmetry is, and that's 90 degrees. Every time I turn it 90 degrees, it'll match up again. Sometimes the way this is asked, and this is up here, it says this, sometimes it'll say, name all angles at which the figure maps onto itself. Well, then I would say 90, 180, 270. I'm not going to list 360 or 0 because that's the starting place, and we know that we're back at the starting place at 360. So we're talking about angles really between 0 and 360. That's what we're interested in. Okay, let's look at this figure. This figure has no rotational symmetry at all because it's pointing to the right now. If I start turning it, and I think this time I'm just going to turn the paper. If I start turning it, now it's pointing down. Now it's pointing to the left. Now it's pointing up. It's not until I get all the way back around that it looks the same, pointing to the right. So that's not rotational symmetry. However, hopefully you noticed as this star was rotating, it should look the same, several different places. So let's look at the star. I'm going to trace the star on my transparency paper. And I already went over the edge a little bit there, not the most accurate tracing. And I tried to fix it, and I don't know that I did much, but that's okay. All right, so let me make this a little bit taller than the other ones, just to point out this was where I started with that pointing up. Okay. Now, it looks fine there. Now, I've rotated just a little bit. I haven't even rotated that much, and it matched up. I'm going to rotate again. Here it matches up again. And rotate again. Here it matches up. How many times do you think? Well, look at how many points there are. There are 5 points. That's going to be 5 times. It matches up perfectly. And 360 degrees divided by 5 will tell me what each angle is. So here I've got a rotational symmetry of order 5. And the angle of rotational symmetry is 360 divided by 5. 360 divided by 5 is 72 degrees. So every 72 degrees, this will match back up. In other words, from here to here, is a rotation of 72 degrees. So if you were asking me, name all the angles at which it maps onto itself, I would say 72. And then the next one would be 72 plus 72, which is 144. And then the next one would be 216. And the next one would be 288. And then we don't have to name 360 because that's pretty much understood. All right, let's go ahead and do our little Ghostbusters band symbol. And I'm not going to trace it that painstakingly. I'm just going to draw a big circle and a little slash mark. Okay? And see if I spin it about itself, about its own center, rotate it in place, whoa, without taking this paper with it, if it ever matches up before it gets all the way back around. And yes, after 180 degrees, in other words, this, let's go ahead and say, this is up. When I rotate it 180, so that up is down, now it matches up. Or it matches, not to use the word up in a different context. Okay, so that means that we have rotational order 2, rotational symmetry of order 2, because there are two places, when this is pointing up and when this is pointing down, that it looks the same. And 360 divided by 2 is 180. So this has order 2, and 180 is my angle of rotational symmetry, a lot like this one up here. Now this one should have a little bit more than the others because it had more lines of symmetry. So we've got a 6-pointed star here. I'm going to, I'm running out of space on my little transparency I'm using here. Trace it. Now this star is, I believe, a little bit compressed vertically. So I don't know that it's going to look perfect, but we're going to pretend it's pretty symmetrical. Okay, so go on a journey of imagination with me. And let's say that this is up. How many times do you think it will match up to itself if I count the starting one as 1? How many points are there on the star? Well, 6-pointed star, we should be able to find 6 places, 6 positions in which it looks the same. There's a second position. See how, it's not quite, but you get the idea. Third position. Fourth position. Fifth position. Sixth position. And this was my first position. So you can kind of think of it as this point moves through these other points, and each time it lands on top of another point, we have an angle of rotational symmetry. So in other words, when it goes over here, up, matches up again when it's on top of that. Then again, when it comes over here, it matches up again, and so on. So there's 6 times, or 6 different ways I can turn this figure, and it looks exactly the same. So that's order 6, and that means that I divide 360 divided by 6 to find my angle of rotational symmetry is 60 degrees. So every 60 degrees that I turn, it's going to match up again. So that means at 60 degrees, at 120 degrees, at 180, at 240, and at 300. And that, my friends, is rotational symmetry in a nutshell. Hope you enjoyed it.